going on. Hopefully we can hear me at the back, and hopefully this thing can hear me as we start. And chapter 1, again, is this introduction to the basics of organic chemistry from the general chemistry perspective. We have this long list of things that you should know coming into the class. I did send emails out periodically over the summer to make sure that people who haven't had general chemistry for a while do some background reading, so we're not starting cold here. We have some idea of how this stuff works. And what I plan to do in the next, well, today and Monday, maybe a little bit of Wednesday, is get through that list. And again, on Wednesday, what we tried to lay out is the sort of way you succeed in this class is by keeping up with it and making sure you're progressing day by day. It's not a good idea here to be waiting until the last minute. If you're a procrastinator, this isn't going to be much fun. But these are things you should know, and we'll find out as we go. We have a periodic table. This is one of the best, most brilliant pieces of organization that humans have ever put together. You look at all the elements there. It's a big, busy piece of work. Can you memorize this thing? No. I have no idea what's at the bottom. I'm not interested in those elements at the bottom. I probably studied them in high school, but since then I don't care. I'm interested in the top right-hand side of the periodic table, because that's where carbon is, and that's where most of the elements are that it will bond with. We do need to worry about some metals. We will talk about bonding in terms of electronegativity and how you can predict the bond in the near future. But that periodic table is there to help you. And on every exam I give, and I think some of the other people do this too, there's a periodic table on the front page. So if you need to check to it, do so. But what you'll find now is that speed will be important. If you're spending 5 minutes trying to find bromine on that periodic table, this isn't going to work. If you roughly know where bromine is, it's on the right-hand side, we're on the way. If you know where the metals are on the left-hand side, good, because then we can start to talk about their properties and why they interact the way they do. Why do they form ionic bonds where atoms in the middle form covalent bonds? So again, this is just a sort of gentle introduction to get started in terms of getting people on the same page. Now, you should have seen this along the way. This governs everything, right? Having said there are no calculations in this class, we do have to worry about some numbers, relative sizes of numbers. We have to worry about concepts mostly, but there will be some numbers involved as proof and as evidence for chemical reactions and why they work and how they work. So, hopefully you've got the slides in front of you, or feel free to copy down. Don't copy all of that. You've got this information at home if you need it. This is really important, this idea of free energy and how molecules express themselves in terms of their energetic properties. We have this combination of what's delta H, which is enthalpy, and delta S, which is entropy. And they're similar and related. One is a temperature-dependent factor, the other one isn't necessarily. And we'll, over the next few weeks, get a handle on why this is important to a chemist and a biochemist later on. We'll see now that enthalpic properties, such as bond energies, will have some bonds that are weak and some bonds that are strong, some of which you'll have to learn. And then to be able to use those numbers to predict what will happen. If you heat a molecule up, which bond is going to pop first? Which one will break first? And it will be the weakest bond. If you know those ideas, it's straightforward. We'll talk about entropy, and we'll talk about this idea of organization or disorder, or the expression of energy in a molecule from an organic perspective. Why are some reactions entropically favored, but enthalpically disfavored, and the other way around? Really key here, and again, I'm saying this in my way so that you get used to it, is this idea of stability and reactivity and their relationship. Stable things tend to be unreactive. Reactive things tend to be unstable. Those ideas then become really sort of intimately tied together when you have to consider a possibility of one chemical reacting with the other. Are they stable? If yes, they probably won't react. If they're reactive for some reason, you will learn they're going to react and give you products. That's the very first thing you have to worry about in terms of a chemical reaction. So this is just to introduce it. If you've seen this before, great. If you haven't, you need to go back in your Gen Chem notes and have a look and read the textbook on this and start to appreciate that everything we do here is driven by energetics. We do some history. We talk about the idea that organic chemistry means nothing anymore. I believe Berzelius was French, and he came up with this idea 200 years ago, that organic chemistry was basically compounds isolated from nature. And that meant that only really animals or plants could make these compounds. And that was blown away not too long after by Wohler in 1828 with the sort of seminal experiment where he mixed chemicals together in the lab, inorganic chemicals, and he made an organic molecule. So all of a sudden you didn't need this vital force. You didn't need something to be alive to be able to make an organic compound. You can mix it in a flask and you get an organic product. So organic means nothing. I wish they'd relabeled it early on, because organic now means things like bananas and stuff in the grocery store. You're an organic chemist, it doesn't mean anything. I think molecular engineering is the way to go. Molecular engineering is really what we do here. So we talked about simplicity and complexity, and how do you go from what is a fairly sort of hopefully solid but sort of lower level understanding of chemistry to being able to look at something like that. Whereas, what do you do along the pathway to get from one to the other? Everybody should be able to look at urea and think it's fairly simple. It doesn't have many atoms. There are none of these wedges and dashes that will mean something later, in which we have stereochemistry in terms of direction and space. The atoms are pointing in different directions. So how do you, as a sort of a beginning organic chemist, get your head around going from the molecule on the left to the molecule on the right? Well, that's the 2 semesters, all right? And we're going to see now that it can be done. If you learn the basic rules and you apply them sensibly and you practice, it's very straightforward to go from the left to the right and to be able to look at molecules on the right and be able to understand them. So looking at the sort of historical perspective here, the whole point was that on the left you have an inorganic molecule. Inorganic meaning it's, it's a rock or it's a salt, something like that. And on the right you had urea. And this was the first experiment that was done and proved that organic meant nothing anymore. So urea itself, fairly simple. It does sort of typify the very basic organic type of structures in which you just have covalent bonds and you just have elements from the right-hand side of the periodic table. You have carbon, nitrogen, and oxygen. And you will spend a lot of time this week learning those 3 elements. What they look like, what shapes they adopt, what their electronic properties are, and how those electronic properties are expressed in a molecule. Because we'll find very quickly that the atomic structure from the periodic table often doesn't match what's happening in a molecule. There has to be some modification, something we call a hybridization model, to be able to explain that along the way. So we're going to start very quickly with this idea of valence. You've seen this before, but now we're focusing on a certain part of the periodic table. On the, the important part here is carbon. If you understand that the maximum number of bonds carbon can form is 4. As we work our way through, people like to put 6 bonds and 7 bonds and 8 bonds, and that's just wrong. Okay? It only needs 4 bonds because it only needs 8 electrons. 2 electrons in each bond, 8 electrons, that's it, 4 bonds. So your typical carbon, when it is neutral and isn't missing a bond or isn't missing any electrons, is 4-valent. We can draw it as we've drawn it there, which is sort of a simple first year type depiction, but we'll see very quickly that that structure is not correct. The way that's drawn like a cross is incorrect. We have to put some more detail in when we talk about electronic properties in the near future. Nitrogen has 3 bonds. If you understand NH3, ammonia, from freshman chemistry, you can do an awful lot of organic chemistry, because all we do is swap out some of those hydrogens and put organic pieces on. Those organic pieces don't do anything chemically. So if you understand the shape of NH3, the chemistry of NH3, the fact that it's a base, and later on we'll call it a nucleophile, if you understand that very simple molecule, you can extrapolate that to organic chemistry. That's how you start to learn this stuff and pick it up, and it can become fun. Oxygen, what's the simplest oxygen molecule you know that looks like that? Water, H2O, right? H2O. So if you know something about water, you can do ether chemistry, you can do alcohol chemistry in the organic realm, because those molecules adopt the same shapes, and they have very similar chemical properties based on having 2 lone pairs. So those are very simple. You should know those coming in. If you don't, go and get comfortable with them, and we'll talk about where lone pairs go in a minute. And if you're okay with that, we're in good shape. On the right-hand side, we're talking about the halogens. They tend to have 1 bond. Hydrogen tends to have 1 bond. And those are very simple things that you should pick up very quickly. Carbon doesn't have 5. It can have 3 later, but right now we're talking about 4 is the maximum. The maximum for nitrogen is 4 actually, but we've got 3 bonds right there. And for oxygen, the typical neutral molecule has 2 bonds. That's as simple as it gets. So how do we put these things together? A lot of this is common sense. And again, you've all hopefully passed the freshman class and you got something out of it. The idea of molecules coming together, or atoms coming together to form molecules based on the need of something, the need to form an octet, the need to get to some stable configuration. But this organic world gets very big very quickly. And if you look at that first molecule I gave you, the Mosaveghi molecule, that's just got dozens of atoms in it. But they've all got set shape, and they're all well understood shapes. If you come to this and you think about, well, there's a formula. You're given some sort of formula to work with. And you don't know the arrangement of those elements. You don't know how they're bonded together. Very quickly, you should be comfortable with doing this type of thing. Okay, I just said carbon has a maximum of 4, hydrogen has a maximum of 1, chlorine has a maximum of 1. You should be able to put that molecule together in some form very quickly to give a sensible molecule, in which all the bonds have the right valence, all the atoms have the right number of electrons, and that's a stable molecule. The problem is people tend to just forget what they know, and they start doing really weird stuff like this, right? What's the problem with that? Do we see a problem with that? Hydrogen bonded to hydrogen, bonded to hydrogen, bonded. Yes, if you don't see a problem, we need to talk. Yes, if you do see a problem, we're in good shape, because that molecule is absolutely nonsensical, because it breaks the rules. Hydrogen can only have 2 electrons, and this molecule I've got a hydrogen with 4 electrons. That's silly. So very basic stuff, sort of a starting point. If you're doing stuff like this, we really need to talk. If you can put that together, we're in good shape, because you've understood something from the freshman classes. Everybody okay? Questions? Ask questions along the way, because I'll just keep going. We go back a little bit, we talk about atomic structure. This is old stuff that you've seen before, but it's important now to understand where we need to go with organic chemistry, because we have to change the shapes of things soon. We have to explain natural shapes and adopt or adapt some of the material you've seen before. You're okay with the idea of 1s2, 2s2, the idea that orbitals fill up before they fill up singly before they double up, but once this is full, we go someplace else, yeah? We go further away. And we can talk about energy, which is going to have more energy, N is 3 or N is 1? Which is going to be further away from the nucleus? N is 3, right? Further away, not held as tightly, easier to give away, okay, more energetic, and they'll be higher in energy. And this is a very simple model to show you those numbers, the energy levels, 1, 2, 3. Now, in the past, I remember freshman chemistry and I remember general chemistry, you had to do 3D, 7, and all this nonsense down there in the forest, in the periodic table. We don't go there. Yeah, we don't have to go into that stuff. So you don't worry about d orbitals anymore. You don't worry about f orbitals. It's all s and p, which is nice. So once we start thinking about how molecules come together, the atoms are looking to become more stable by interacting with some other piece, some other atom or group, to give something more stable. And we could argue that a hydrogen bond between two HH atoms is very strong. It certainly is. It's difficult to break because it's very strong. We'll have to worry about some numbers and their magnitudes. So hydrogen's a strong bond. It's about 436 kilojoules in real money. In calories, it's about 100 kilocalories. And we'll work with both because you need to be conversant with those these days. That is a strong bond. It makes sense. You've got two elements on the right which are unstable, and they came together to make something stable. They both now have the right number of electrons in that molecule of H2, and so that should be difficult to break. We went downhill energetically, we'll talk about that in the near future, but now we have a pretty strong bond. And the argument goes that those two atoms are going to be comfortable at a certain distance from each other. If they get too close, they start to repel. If they get too far away, the bond starts to break. And you don't even need to worry about this graph. It's just saying that there is an understood, predictable bond length between those two hydrogens based on their comfort zones. We'll talk about bond lengths. We'll talk about bond energies. We'll memorize some things that will help. But for the most part, it's the same idea. Elements react to give you more stable outcomes. In this case, the more stable outcome is the H2 molecule. So what do we deal with here? Not an awful lot. You can summarize organic chemistry by that part of the periodic table. You're going to see some of the little bits and pieces in the middle, but not an awful lot. A lot of this stuff is going to be top right of the periodic table, some halogens and some metals. You mix them together, understand the basics, and away we go. So we need to worry about how we can use this periodic table to help us get started with electron configurations. You realize that this table was put together so that elements with similar properties were lined up next to each other or on top of each other. And as you work your way across the periodic table, things start to happen. You start to add more electrons, you start to add more protons. Atoms tend to get a bit smaller because they're starting to get a bit tighter in terms of being the electrons being held. And as you head down the periodic table, what happens to size? Do we get bigger or smaller heading down the periodic table? We are adding more electrons heading down. So does it get bigger or smaller? There's a kind of a clue there. It gets bigger. It gets bigger, right? Those are simple things that you should know. If you don't, we're going to have problems. I need to make sure that you understand the way organic chemists write these things. It's amazing how different professors in different countries and whatever will express these very same things very different ways. We need to worry about organic chemistry, and this is pretty much uniform. That is an expression of the very simplest element, hydrogen, working your way through helium, lithium, beryllium, boron, carbon, all the way down to magnesium. And what we're doing here is adding electrons to energy levels. We start off with 1s, we put 1 in there, that's hydrogen. You go to 1s2, that's helium. You go to 1s2, 2s1, that's lithium. You've seen this before. Obviously, for this class, we're going to spend an awful lot of time here, and here, and here, and probably there. But we're now starting to see things that I know some of you haven't seen before. I know some professors don't teach this, the idea that at the 2p level, there are 3 equivalent orbitals that are 90 degrees to each other. They're orthogonal to each other. And they express themselves along the Cartesian coordinates, x, y, z. And why do they do that? Because that's the furthest way they can get from each other. You're going to have an orbital with electrons in, electrons repel, they try and get away from each other. The furthest they can do that for this system would be x, y, z. So as we build these things up, if we start with carbon, carbon has 6 electrons, we know that from the periodic table, and we fill in the 1s orbital because that's logical. We don't even talk about 1s very much because it's the core set of electrons. They don't do anything, so we don't worry about them. But then we do start to worry about the 2s, the 2p's, and we have to again realize that the 2p's are broken into 3 different valences. So with that in mind, memorize this stuff? No, I can't memorize that stuff. I'm rubbish at memorizing. That's why I didn't do biology. understand that stuff, you just build it up. You look at the periodic table, you look at the number, the atomic number right there, you know you've got 6 electrons, and away you go. And we don't even go any further than that. That's it. We need to worry about definitions. You've all seen this before, I hope at least in freshman chem and probably in high school too, this idea of bonding, this idea of electrons being transferred in ionic bonds or electrons being shared in covalent bonds. Well, you've seen probably the extreme examples where you can say for sure that molecule is covalent or that bond is ionic, because you typically talk about the left-hand side of the periodic table and the far right. And they swap electrons, and that's going to be an ionic bond. But we're spending most of our time in the middle. Most of our time is spent with carbon, nitrogen, oxygen. They're all very close to each other in the periodic table, but then close to each other in electronegativity. And it's electronegativity that will dictate what type of bond we have. That's going to be useful because then you can go further and predict stuff you haven't seen before. We do have to worry about carbon bonding with metals. There's a huge amount of organometallic chemistry that we need to worry about, and that will then test you because, okay, is this a covalent bond? Is it an ionic bond? Or is it somewhere in between? I bet you haven't seen somewhere in between before. Very highly polar covalent bonds. That's a big deal in terms of understanding organic chemistry. But you can get a handle on this if you understand electronegativity. And I'm going to assume you don't know anything about electronegativity, and we'll start from scratch. It is the attraction of an element or a nucleus for electrons. Okay? So what's the most electronegative element we have? Fluorine. What's its electronegativity on the scale? 4. And what about the metals? Are they high electronegativity or low? Low. I'll give you some numbers and I will ask you. No, I will tell you to memorize them because you will be able to use them very quickly to understand the type of chemistry that you should be expecting to do based on the differences. So we'll build on this. We've got 27 chapters to build on this stuff. We'll start thinking about the obvious ones that you know. Sodium chloride, all day will be ionic. CH4, all day will be covalent. But we're going to mix things up. We're going to see molecules that have both, and you've got to worry about where the electrons are. So when we're starting to build molecules, a lot of this does come from a very simple understanding of the periodic table and why it was put together the way it was. So you look at something like ammonia. We're now putting the dots in. Now the dots are important, but very quickly in organic chemistry you recognize that the dots become a problem if you try and put them all in. If you're trying to put all the dots in the bonds of that big molecule I showed you at the beginning, you'll be here until December. It takes forever. So we'll see some shortcuts, and those shortcuts can be very useful, but they can also be problematic if you don't understand it. You'll find now that if you're trying to build a molecule with these elements, the only way you can do it is that. If again you're putting hydrogen next to hydrogen next to hydrogen next to nitrogen, we didn't learn anything in freshman chemistry. If you can put ammonia together very quickly, we have a molecule, which does represent more complex molecules later on. What we'll see very quickly is that these dots become prohibitive. We don't draw all the dots. Part of chapter 2 is trying to go backwards and getting rid of those dots and putting in straight lines so that we can speed things up and draw molecules quickly. The only dots you have to worry about will be lone pairs. So you'll notice on water and on ammonia and on HF down there, we do have the lone pairs in there. Those lone pairs need to be there because they are the chemistry, that's where the chemistry will happen. Lone pairs are sticky. They stick to things. They stick to protons, they stick to carbons. So you need to represent where the lone pair is so that we can use it in a mechanism and use it in a chemical reaction. But those are things you've seen. If you can put those molecules together, we're halfway there. We have to worry about detail. This gets people at the beginning. It's very straightforward. You start to recognize these things quickly because organic chemistry largely is pattern recognition. If you see a monovalent oxygen, it's going to be negative. And I've always thought, I had really good people in high school who taught chemistry, and they always referred me to very simple things. Reduce things to the most simple form, and then you know what you're doing. The only difference between this molecule on the left and this molecule on the right is the carbon and those hydrogens. And I'll tell you right now, those carbons and those hydrogens don't do anything. They're chemically inert. It's the oxygen that's the business part of that molecule. So if I understand that this is a monovalent oxygen, it only has one bond and it has 3 lone pairs, that's different to water. Water had 2 bonds and 2 lone pairs. This is chemically different because it has 3 lone pairs and only 1 bond. So I always refer quickly back to high school. Hydroxide only has 1 bond. What is the charge on that oxygen in hydroxide? What is the charge in sodium hydroxide on the hydroxide bit? Is it negative or positive? It is negative, right? So it's got a -1. I'll show you where this comes from, how you can calculate it and predict it without a calculator. But that hydroxide sort of exemplifies where we need to go. This molecule on the right, methoxide, has very similar properties to hydroxide. If you put your hand in this stuff, it hurts. If you spill it on yourself, it hurts, just like hydroxide does. So chemically, it's very similar, and we've got to worry about now, why am I doing this? It isn't water. It doesn't look like water. It's not neutral. So I need to put some charge in here. I'll tell you now that the charge on that oxygen is -1, just like it was in hydroxide. You know hydroxide, extrapolate. You can put whatever you want on the end of this thing. You can put long, long chains, you can put elephants, whatever you want on the end of this thing, and that is always going to be a 1 negative charge. You start to see these things, organic chemistry demystifies very quickly. So where does this -1 come from? Why do I need -1? Well, think about this conceptually. If the molecule is neutral, and you have 2 lone pairs on the O, if you put an extra lone pair on that O, do you think it becomes negative or positive? Just conceptually, negative, right? Because electrons are negative. Now you can calculate this and actually quantify it by doing this idea at the bottom. You can learn this straight off. It's helpful. But you'll see patterns. The more you practice, you'll see patterns. Group number. Group number, I think oxygen's in group 6, right? So that's 6 minus the number of bonds. What's the number of bonds for that oxygen? 1. So 6 minus 1 is 5. And how many unpaired electrons on that oxygen right there? 6. 6 minus 1 minus 6 is -1. That's where that came from. Learn it, practice it, it's useful, but you will start to see the patterns as we go. And this is where recitation will come in handy for the most of you who are in recitation. We can practice these things all day if you want to. More complex molecules, these are just examples of where we need to go. Nitric acid isn't very simple because it has odd-looking valences. It has a nitrogen with 4 bonds. The typical molecule you deal with nitrogen is NH3. This isn't NH3, it's got 4 bonds. So something's up. It's sharing more electrons than it was in NH3. If it's sharing more electrons and giving more electrons away, it isn't becoming positive now. I'm sorry, it isn't becoming negative, it's becoming positive. That's where that positive charge comes from, but you can calculate it. So, knowing your periodic table, nitrogen's 5, minus number of bonds there is 4. No unpaired electrons, because that would break the octet rule, and that's +1. That's where that came from. If you look at the oxygen, it's got a 1 bond. From what we just did, 1 bond to oxygen, 3 lone pairs, that's negative. Just like hydroxide, even though that's buried in a more complex molecule. It's the same idea. Down here, ozone we'll have to worry about quite a bit because it's reactive and it's very useful. It's probably one of the 2 favorite mechanisms you have to deal with in the chemistry class. Look at the middle atom there. Group 6. How many bonds? 3. 6 minus 3 is 3. And how many unpaired electrons? 2. We're down to +1. That's where the number came from. You can practice these things in the book. You can practice them online. And you get very good at them very quickly. But you have to see this. This is going to be useful every day to be able to predict what a molecule will do. So formal charge is important. Why? Because that's not the same valence as a water molecule or an ammonia molecule. They are different shapes with different patterns with different numbers of electrons around them. So you have to modify that. And that's where those charges come from. I'm going to ask you to learn these numbers. I'm going to ask you to learn some electronegativity values. Okay? We're going to talk about this part of the periodic table mostly, and I would like you to know those by yesterday. Certainly by Monday. And I'll ask you questions on them and I'll test you on them. General trends that you've seen before, left of the periodic table, low. Do those elements like to give electrons away or take electrons in? Give them away. Now, if you are highly electronegative, you wouldn't want to give that electron away. So low electronegativity correlates to wanting to give electrons away. Metals. Head across the periodic table, we get to the business side. We get to carbon, 2.5. You'll remember that for the rest of your life. I will run into you in Giant Eagle one day, and I will ask you what the electronegativity of carbon is. And if you don't tell me 2.5, there'll be trouble. You need to know these things, okay? Tattoo them on the inside of your head. Nitrogen, 3.0. A little bit more electronegative. Why? Well, we added an extra proton. We did put an extra electron in, but it's at the same energy level as the one before it, so it's held more tightly. And we go across, we get 3.5 for oxygen, we get 4 for fluorine, and we have a nice system now to be able to discuss relative electronegativities. So the trend is the electronegativity is increasing across the periodic table. You've seen that before, I hope. As you head down the periodic table, the electronegativity seems to drop off because the electrons are going out into higher energy orbitals. The electrons are getting further away from the nucleus. They're not held as tightly. And that nucleus now has less influence on these electrons over here. So it's less electronegative. Well, we can use that. I'm going to talk about this again as we work our way through the class, but you should know those numbers. And you should have some idea of what we can do with those numbers to be able to understand chemistry. So at the bottom I have this random collection of molecules. I'm not going to do much of any chemistry today. We're going to start understanding things. I have hydrogen, HF, H2O, CH4, which is methane, and chloromethane, CH3Cl. You haven't seen many of those before. But we can very quickly start to understand their chemical and physical properties like you would for the lab by looking at electronegativities. So I have some announcements to make, and I'm going to talk to this and then go back to that announcement. I've drawn these molecules out. You should by now be able to draw those molecules out, as I've shown like that. H and H, H2. So electronegativity values lead to something called induction and something called a polar covalent bond. It's a very simple concept if you get it. It's tricky if you know, if you have to think about this. From that slide that I just showed you, the electronegativity value of hydrogen is 2.1. And the electronegativity of that hydrogen is also 2.1. If it wasn't, ugh, you couldn't learn this stuff, right? It's 2.1. The question I've got for you is that bond in the middle, which is a single bond, is a pair of electrons held between the two atoms. Now, with those two electronegativity values, where are those electrons? Closer to H on the left, closer to H on the right, or about in the middle? About in the middle. You get that? We're on our way. Because they have the same pull on those electrons, so they're equally shared. If I move over to methane, I had 2.5 as my carbon electronegativity, and I have 2.1 as my hydrogen electronegativity. Here's where we've got to be careful, where we need more detail, which is what we'll build up in the second chapter. If you had to say from what you know right now, where the electrons are in those bonds, are they closer to C or closer to H? Closer to C, but how much? Not much. Those electronegativity values aren't that different, right? They're not very much different, so there isn't that much of a pull. And we'll say that those are actually non-polar bonds. For a small electronegativity value like that, that would be a non-polar bond. On the molecule on the left, definitely. Hydrogen's a non-polar molecule. Now, we head over here. We look at nitrogen over there. 3. 2.1. That gap got bigger. 0.9. Where are the electrons closer to, the N or the H? The nitrogen. So the hydrogen's losing out, and I'm starting to use the terms that we need to worry about for mechanism. The nitrogen is electron-rich. Not just because it has a lone pair, but because it's greedy and it's pulling electrons away from the hydrogens. The hydrogens, conversely, will be electron-poor, because they're losing out on electron density from that nitrogen. That will lead to the vast majority of chemistry in this class. You're going to identify where the positive part is, you're going to identify where the negative piece is, snap them together. That's most of the mechanism you have to worry about. So this is the starting of that. Down at the bottom, HCl. You just know this from your past experience. This is 2.1. I think this is 3. Where are the electrons closer to, Cl or H? Cl. What about in this one here? Where is most of the electron density? Which atom is pulling electrons towards itself? The oxygen, because it's highly electronegative. And on the right-hand side, like water, again, oxygen is 3.5, hydrogen is 2.1. You'll know that over the weekend. You can then start to worry about the properties. So we can do that, and we can write those numbers in, but we have a shorthand notation to do this. In this type of system, we're going to use delta a little bit. Just means a little bit. So if you see a delta positive, it's a little bit positive. If you see a delta negative, it's a little bit negative. All based on that electronegativity difference that we just talked about. So what I've got over here, no need for that notation because those two atoms have the same electronegativity and have an equal pull on those electrons. Here, got to believe me here, that difference isn't big enough. The 2.1, 2.5 isn't big enough. And all the alkanes you'll see, stuff like ethane, methane, propane, those will be non-polar molecules. And you'll see how this builds into the lab. They will not dissolve in water. If you're very polar, you tend to dissolve in polar stuff. If you're non-polar, you tend to dissolve in non-polar stuff. And you'll learn in lab this idea of like dissolves like, which will stick with you forever. On the right-hand side, I did talk about numbers, but now I'm using this sort of shorthand notation. Those hydrogens are all delta plus. That nitrogen is delta negative, simply based on electronegativity differences. And now we can talk about polarity within bonds. And that sets up the chemistry to happen. So know those numbers, and then you should be able to, for example, on a first quiz that will come up in recitation fairly soon, be able to put those in. Anybody want to say anything? Go ahead. There's a range. That is the one that you typically say is definitely non-polar. The one that will be problematic later might be something like bromine, which is 2.8, and carbon next to it is 2.5. But that bond is slightly polarized. And it's more to do with the size difference between the elements. Right? So that detail, there is no absolute. I can't say for sure that this is not polar or this is polar. Right? It'll be experience as we build our way through. Okay? That was our first question, ladies and gentlemen. Well done. Next, go on. Yes. So the question is this also delta plus and is this also delta plus? The answer is yes. I typically set up this type of question by focusing on one bond. If you can understand the one bond, then I assume that you understand the rest of them are similar. Yeah. It is. Yes, the H is next to a carbon. The H is next to a carbon. Okay. And if you want to look at this, I mean, this is going to be 3719 in the next week or so when we do acids and bases. This is 3720. And this is 3719. And they're all very similar and they're sort of cut and dry. The really tricky stuff comes later. Yeah, but there are other things, like I just said, about size differences that will play a role in that. Okay, but we've got, why are we here for 9 months? There's a lot of detail here. Go ahead. Yes, it is. Yes, it is. It's that arrow, isn't it? You've got that arrow there, and sometimes you do that. That's the same sort of thing, yeah. Yeah. Now, we're not done with this by a long stretch. This is just introducing the language to get everybody on the same page. So that's kind of fun. I'll mention this now that everybody's awake. I know some people have already dropped, which is kind of interesting. Dr. Jackson tells me that labs begin next Monday, so please show up to your lab next Monday and days afterwards to make sure you get signed in and what have you. Some of you are not signed up for Wiley Plus. I don't know why. 111 are, 32 aren't. And I'm keeping a track of this, who signed up and who didn't, when it comes to grades at the end. Did you fail? Well, you took a month to sign up for Wiley Plus. Did you fail? You weren't in recitation. Did you fail? You never came and spoke to me. We never got problems solved. So get it organized. Get on there, do some problems. Over the weekend, you can do the Orion stuff. You can try the homework. Just get used to the system so that you're not panicking next week when things are due. I would try some Orion. At the bottom of your dashboard, when you open that page, is that Orion stuff. And I looked at the grades this morning. Some people are really struggling with that stuff. That's freshman chemistry stuff. If you're struggling with that stuff, we need to talk as soon as possible. If you're getting less than 50% on those questions, we need to talk. It doesn't get any easier from here. So again, check your email. If you're getting emails from me in the near future, it might be because of that. Come and talk to me. Let's get problems solved. Tyler 3000 there is teaching SI next week. We're not quite sure when. Yeah, we'll tell you on Monday. We'll have a session. And you can get more practice doing that. And we can also think about recitation. I will give you a quiz in recitation. I'll talk about that more on Monday. It'll be online as well. Obviously, the class stuff is homework. And the recitation quiz will be labeled as a quiz. If you're in recitation, you need to be doing those as well. Everybody okay with that? Okay. So we've already very quickly started to look at organic molecules and sort of extrapolated from the freshman stuff. We've gone into the bigger world. This is important. This is one of the key factors you need to worry about. You need to worry about how many bonds can be formed. You need to worry about where lone pairs are. You need to worry about any charges in a molecule, and you need to worry about polarity. And polarity is a really important system. It's a really important idea here. So moving along, there's the book. It has what I call a continuum of sort of polarity. You have the different polarities starting at very nonpolar with little electronegativity differences, and then at the right-hand side you have big electronegativity differences. Now, I'm probably too old to write my own textbook, but when you read new textbooks, you always think about, what went wrong here. What's the problem there? Anybody see a problem with that bond or a problem with that bond? It's a typo in the book, or they just overlooked it. What's wrong with those bonds? Are they really covalent bonds? Should there be a line between those atoms showing a sharing of electron density? From your past experience, NaCl, is that covalent? No, it's not. So that's just a little typo. Same with oxygen. That's not going to be polar, and that's not going to be covalent. That's not going to be covalent. But that's what you will learn. As you practice, you will pick this up very quickly. And you'll have a rough idea of where to cut things off. This is definitely covalent. This is definitely ionic. You'll learn that as you go. Okay, examples. Organic systems you haven't seen before. Very quickly. All of this is carbon and hydrogen. You expect it to be polar or non-polar? Non-polar, no delta plus, delta minus. Over here I have a bunch of oxygens and nitrogens. Do I have any delta pluses in here? I would think so. Do I have any delta negatives? I would think so, right? So you practice those things and we should be okay. Alkyl halide's a little bit different. Chlorine's about 3. Carbon next to it's 2.5. So there will be a delta plus, delta negative setup right there. And 3720 mostly is based on delta plus on that carbon and delta negative on that oxygen next to it. It is really important you get this really quickly. Am I going too slowly? Because I can speed up. Hello. What's up? You don't. Okay? This is my attempt to get you starting to think about these things, and I'm transitioning. That's a very good question because this is what organic chemists write. You're used to, in the other classes you've taken, writing carbon, hydrogen, carbon, hydrogen. I don't have time. Chapter 2 is all about coming up with those pictures. But if I tell you it's all carbon and hydrogen, you should be able to work out that it's not polar. Yeah. So we're just sort of getting started, and you'll see very quickly how to put those things together next week. Right, back to bonds, back to atomic orbitals. I want to try and get some of this done today so that you have the weekend to think, what on earth just happened? And then we think about it again on Monday, and we make sure we get it, because this is not easy at all. Physics, doesn't really matter if you've had physics or not. We have to worry about bonds, we have to worry about things coming together, and we'll find that when two atoms come together, they have two choices, either bond or don't bond. We form a bond or an antibond. Have you all heard of antibonds before? We know what an antibond is. It's a space that you can put electrons in later on. One is stable, one is unstable. You're going to get the stable one, right? But the other one also exists. We need to worry about shapes of orbitals. We need to worry from the freshman stuff, an s orbital is spherical, a p orbital is this kind of dumbbell shape. And we need to think about things like nodes. What is a node? What is at that node right there? These are orbitals, or these are lobes of orbitals, and this is where I can find my electrons. This is where I can find my electron. What's at the middle right there? The nucleus. Yes, that's where you're not going to find the electrons because that's where the nucleus is. So those shapes are very straightforward, and you've seen them before. 1s, spherical. Be very careful here. These are not basketballs or real footballs where you can kick things. This does not have a case. This does not have a coating. This is just a volume in space that you'll find these electrons. As you move from 1s to 2s, the 2s gets bigger. The electrons are further away from the nucleus, not held as tightly, more reactive, and they'll be now valence electrons. So you know this. As we move into the p orbitals, maybe you don't know this one because you didn't see it before. We have this Cartesian coordinate idea where we have x, y, and z, and those three p orbitals project themselves along those lines so they can get away from each other. You'll find now that you put electrons into orbitals, electrons are negative, they repel, electrons want to be away from each other, so orbitals want to be away from each other. So we'll see 2s, 2p, and we'll see 1s, but we really don't mention 1s because it's inert, it doesn't do anything. So I've got this word here that we'll need to use in the future, degenerate. It just means they're equivalent. The 2px is the same as the 2py is the same as the 2pz in terms of shape and size. The only difference is their projection in space, the direction they're projecting. And we'll have to fill them up. And then once we've got them filled up for the elements, we'll have to start thinking about how to put them together in molecules, and that's where it gets tricky. But once you conquer this, it's kind of fun. There are the basic pieces we need to worry about. Don't worry about D or F or anything that you've seen before like that. This is where we deal. This is where we play. So there they are, my shapes. You need to see what they look like. You need to understand where they are. And then you'll have to worry about how they interact. How do you put a pi bond together with p orbitals? How do you put sigma bonds together with s and hybrid orbitals? And that's where we need to spend most of our time. So I have this notation. Some of you have seen this before, some of you haven't. As an organic chemist, I'm comfortable with this. That's my attempt at an electron configuration. The 1 is the energy level, the s is the orbital, the little one, superscript, is the number of electrons in that orbital. And then I'll extrapolate that further with an energy diagram in a second. So as I move down to carbon, it's getting more complicated. You absolutely must know carbon. And if you do know carbon, you can know the others because they're either one fewer electron, one more electron, two more electrons. It's not so difficult. 1s2, 2s2, 2px1, 2py1. I'm not that interested in those electrons because they don't do anything. I want to do chemistry, which is change. They don't change. I have s, and I have p, and I have p, and I still have a 2pz orbital, but it's empty. I might need to put something in there later, but it's not being used for that atom. Understand that notation, understand what the superscripts mean, and we're good. This is different. Have you ever seen things like this before? Some of you have, some of you have not. Organic chemistry is all about energy, and we have to keep that in the back of our mind. You have to worry about stability, and you have to worry about reactivity. And a very simple way to do this is to do it graphically and pictorially. To have different levels of energy, to populate different orbitals of different energies to talk about their relative reactivity. So the 1s will be very low. It's very close to the nucleus, it's held very tightly, not very energetic, can't do anything, low energy. So if I would look at carbon over here, there's my electron configuration extrapolated from that previous table into what I call an energy diagram. And on the first exam, you always have these pictures. You always have to fill these things in. So you can't get away from this stuff. It will be on your exam at some point. What I've got here is an expression of energy, as that axis, and then I have these horizontals. And what you need to get out of today and over the weekend as you read is that the horizontal lines here are the orbital. They are the volume in space in which you can find those electrons. The little arrows are the electrons. So understand that, label that, make sure you're okay. That is an orbital. They are electrons. So for carbon, I can express this as 1s2, low energy, 2s2, higher energy, and then degenerate, which means the same energy, same shape, degenerate p orbitals, 2 of which are half full, 2 of which have 1 electron each. If I were to put an extra electron there and go to nitrogen, where would it go? Would this make sense for nitrogen? No, because you fill up singly before you double up, so it would go over here, and then you'd start doubling up, and if you do so, you'd end up with oxygen. And you go further, you end up with fluorine. And it's a simple process to be able to add those electrons to get the different elements. So understand the horizontals are orbitals, the arrows are electrons. Well, that's freshman stuff. What we need to worry about is the new stuff. And this idea that when elements come together to form bonds, it's either good or bad. Mostly it's good. They start out high energy as individual elements, they bond together, they give you a bond which is more stable. And you can express that as a bond energy. These two pictures here, don't even worry about this. I mean, the equivalent of this is being at the beach and it's maybe windy and the waves are started hitting each other and sometimes they hit each other and get bigger. That's constructive, and sometimes they hit each other and they cancel out and it goes flat. That's what's happening here. As a chemist, the constructive interference is the bond. That's the good one. The destructive interference, when they don't overlap properly, that's the antibond. So I'll never be drawing those pictures. I'm going to be drawing pictures like this. What does a bond look like? You can map these things on a computer. If you download the ChemDraw software that I talked about the other day, you can make these things and you can see the electron density maps. You can see where the bonds are. So we're not going to see that in great detail because we're going to draw little lines. We don't have time to draw all these things, but you need to worry about what they look like. So in this example for a hydrogen molecule, I've got a 1s orbital here interacting with a 1s orbital here. They both had 1 electron from atomic hydrogen, and they came together to give me an H2 molecule, in which the electrons are roughly equal, well, they are equally shared because they have the same electronegativity, and that's a different way of drawing hydrogen. But we always refer to this because it's the simplest example. If we understand this, we can start to extrapolate to more complicated molecules, which we'll have to do right now with things like CH4. So what I'm going to say is that we will see 2 orbitals, 2 types of orbitals in any bond, one of which is bonding, and the other one is which is said to be anti-bonding. This is, again, a sort of pictorial description of energy. I'm starting off. The language here is important. I would call this my ground state. Okay, this is the 0 point. This is where these atoms are hydrogen atoms, and they haven't bonded yet. So they're fairly high in energy because they're reactive and they want to react. If they do react, they become a bond. And that bond should be low energy. That's the whole point of this stuff. If I do that, I have 1 electron from here, 1 electron from here. It fills up the bonding orbital, and I have a very stable, very happy, very content hydrogen molecule, H2. But we've now got to start worrying, and I will point this out along the way when we get there, about this thing up here. This is the opposite. An antibond to me is like a parking spot. If you want to get to school, you might park on the first floor of Wick Deck over there and walk across the campus and you're in your class. No problem, low energy. But if the parking lot is full, where do you have to go? Higher. You might end up on the 6th floor. You have to walk further. You have to go downstairs and all sorts of stuff. Higher energy. So this is something we'll use later. We'll use that to put electrons in when we need to later, when we do chemistry. Recognize that it's there. Recognize that for every bond you form, every situation of overlap also has this other opposite destructive situation. And there's a general thing from freshman chem. I'm starting with 2 atomic orbitals, and I must conserve the number. So if I start with 2 atomic orbitals, I must make 2 molecular orbitals, one of which is bonding, one of which is anti-bonding. Not happy with that? Ask. Make sure you understand what we're doing here. So for carbon, it's quite a bit more complicated than that. For carbon, you've got multiple bonds. You can see here 2 pictures of CH3Br. CH3Br is very simple, but it's way more complicated than H2. You can see the electron maps where we've calculated these things on a computer, and you can see where the electrons are thought to be and the populations and the density of electrons right there. And this is starting to look fairly complicated. This is a description of a bonding orbital between the carbon and the bromine, and this is the description of an anti-bonding orbital in which there's no electron density between the 2 elements. So we can draw those things in class. We can do them in the first computer experiment that you do in lab in a couple of weeks and see that these things are useful. But we need to do this on a very fundamental level. We need to explain very quickly why the periodic table structure of carbon does not fit this molecule. Should make sense because in the periodic table it's an element, but in the molecule it's part of a molecule. It has changed. It had atomic orbitals in the periodic table. It's now got molecular orbitals in the molecule, and they have changed. So I'm going to start this now. I think I've got 3 of your American minutes. So I'm going to start this, and you're going to worry about this over the weekend because it's going to snow. Stay inside, nothing on TV, get some studying done, and then we'll be happy on Monday. There's a depiction for hydrogen. There's a depiction from the periodic table for carbon. 1s we don't care about, 2s we are going to care about, and the 2p's we are going to care about. And carbon has 4 bonds. So to form 4 bonds, carbon pretty much has to bring 4 electrons. It's got 4 valence electrons. But the problem here is that that bond is the same as that bond in terms of its length. And it's the same as this bond. And that angle between those bonds is the same as this angle. They're all the same. You'll pick this up over the weekend that this type of very simple system like CH4, the central carbon projects itself as a tetrahedron. It's a regular tetrahedron. We'll do this on Monday. We'll do it in the 2nd chapter, in which this looks an awful lot like a triangular-based pyramid, a tetrahedron. And those numbers become something that is important and sticks with you. Those are the bond angles for something like methane. But the problem is, you can't reconcile that molecule with that picture. This has s orbitals, one of which is full. It has 2p orbitals, 2 of which are half full and 1 of which is empty. I would argue that that is not the same as that. Are we okay with that? Those s and those p's are different. So how on earth can this molecule form if I'm using s and p and they're different? If I get 4 equivalent bonds? Well, you're not using these orbitals. There's a model been developed called hybridization. Some I think you've seen before. We need to do this carefully and take our time so that everybody gets it to build up. We're just building up the basics right now. So I'm going to do this now. I'll come back on Monday, and we'll explain it in hopefully again. I need to change the pattern. I need to alter the carbon so that it matches reality. It matches what it looks like in the actual molecule. So to do this, the textbook takes you through this process. I'm not that keen on the way this is described, and I'll explain it differently on Monday. But you're going to mix things up. I'm going to have to take, it's like taking in a blender. You take 3 bananas and you take a tomato, right? 3 of them are yellow, 1 of them is red. And you put them in the blender in the kitchen and you mash them all up. What do they look like at the end? A banana tomato. They look something in between. They look something in between, right? And that's what we're doing here. We're mixing these things up to get 4 equivalent things that are the same. So I'm going to take my s orbital and my p orbitals, and I'm going to mix them together. And ultimately, I'm going to get 4 orbitals the same. I'll explain in recitation why I don't like that, but I'm going to take electrons and mix them all together, and orbitals and mix them all together, and come up with something that matches reality. So your reading has to include this over the weekend. Where do my 4 equivalent orbitals come from? Well, they come from, this is important, don't be going yet. I take an s orbital, and I take 3 of the p orbitals, just numbers, sp3. I take an s and 3 of the p's, sp3, and I smash them all together. And hybridize is just a fancy word for mix. And I get 4 equivalent orbitals, which are somewhere in between the energy of what we started with, and match my picture. The model matches my picture. I then have 4 orbitals, which are degenerate, and now I need 4 electrons because I had 2 from the, I had 1 from here, I had 3 from there, that's 4. I fill up singly before I double up, and I get something called sp3. And that's the beginning of the discussion of hybridization, and we'll carry that on Monday. Go ahead. Hang on. Question? No, I think that's a typo. I think it's a typo. But that's why I'm starting on Monday. Do some work! Get some homework done!
Okay, I know you can't. But, so I talked to Jackson about my lab grade.
Yes.
Sent it to you.